Hello and welcome to this part 2 of So You Think You Can Link. As the title suggests, I assume that you can link and you have been using LINQ for a while, but you're probably not very clear on certain aspects about LINQ, or definitely the inner workings or underpinnings of LINQ, or certain technologies that make or LINQ possible, and certain features that we have available to us that LINQ uses extremely well, but we may not be using them in our own applications or our own designs. And so the sort of motivation for this talk in the part 2 is to kind of explore some of those features, some of those areas, and then look at how we could use some of the underpinning technologies or features for our own applications. In this part 2, we'll be looking at initially inner joins or equijoins, group joins, and left outer joins. Now, I assume again that you understand what a join is. I just want to show you how you would do the joins in using LINQ, and some of the differences, if you will, between how you expect a join to, how you would expect to do a join, say in a database versus in LINQ. Then we'll be looking at LINQ generators. Generators in this case means random number generators or random sequence generators. I think this is a fun topic because it shows you how you can use LINQ for things that you normally wouldn't imagine. I certainly didn't. It's kind of mind-bending, if you will, when you think about, oh wow, how come I didn't think about that? And it's a lot of fun because you get a sense of how LINQ works under the hood, and then how to make or take advantage of that in your own applications for other weird things. I'm not suggesting that you want to use LINQ for weird things, but I think this is a good use of LINQ, but it's something you wouldn't normally have thought about. Next, we'll be looking at iterators. Now, iterators were introduced in .NET 2.0 or C# 2, and but they play a crucial role in LINQ, and so I thought it is best for us to look at iterators. Now, iterators, the feature was introduced in .NET 2.0, but we've had actually the ability to do iterators in .NET 1 as well. Things were quite a bit different in .NET 1 as compared to .NET 2, and so what we want to look at is two things. One is, how would we go about making an iterator for ourselves, and then how would we also support the for each statement in our own types, as in our own custom classes that are not necessarily a collection by themselves, because of course every collection just by default supports for each. But what if you have some custom classes of your own that are not collections, and how would you support for each in those scenarios? Again, the idea is here to give you sort of a foundational understanding of some of the language and compiler features and capabilities in C#. And lastly, in this session, we will be looking at delegates, anonymous methods, and lambdas. Delegates were obviously introduced in since .NET 1.0, so we've had delegates since the very beginning of C#. Lambdas were introduced in C# 3, along with the LINQ features, and LINQ makes heavy use of lambdas. The purpose of this section in this talk, in this part 2, is to explore delegates a lot more deeper, understanding what the compiler does, what the runtime is doing, and then of course the comparisons, if you will, between delegates, anonymous methods, and lambdas. And finally, the real motivation of this whole series, in fact, is to show you how you could use delegates to define your own higher order functions and therefore make most benefit or make best use of delegates for scenarios that we don't normally use them for. And I think that's a sad state of affairs when there's so much opportunity for us to be able to use delegates for higher order functions, and we just don't think in that fashion. So in the next part 2, we'll be looking at much more involved uses of delegates as higher order functions, and also for streaming purposes, LINQ streaming. So iterators are kind of the foundation for LINQ streaming as well. We'll be looking at iterators today in more from the perspective of iterators themselves and how they actually function. But then in part 3 we'll be looking at using link streaming as well as the higher order functions using delegates. So let's get started with some code here. So first thing we're going to do today is the joins and group joins and inner joins. So the inner join or left inner join or equi join, they're all the same. And what we have here is I have two methods here. I have one method that says get categories, and that returns in this case just an enumerable of string, which is, let's call this the categories table, if you will. It's just easier to talk that way. And the second one is a products table, which is returning an enumerable of product. And product has two properties here, the name and the category. And of course, the category is the same as the category that you find in this category table. So there are scenarios where some categories don't have products and products have categories that don't belong on this table, but that's so that we can exercise or show off the joins themselves. But that's a simple data set here. So what I'm going to do now is let me just delete all this so you can see me typing it and kind of get a better sense of how this is composed. So result is equal to from C in categories, which is the categories table, join P in products. So far they're almost the same, right? From C in categories, instead of saying from P in products, you're saying join P in products. And then on C equals P dot category. Now in SQL, you'd kind of do the same thing, except this would be an equality operator here, not some sort of a keyword. In LINQ, the left hand side and the right hand side are expressions. They're not numbers or values that you can equate. So the difference is that because these are expressions, even though it doesn't look like an expression here, this doesn't look like an expression here either. There are two expressions, left hand side and right hand side, and so the equals contextual keyword was introduced in LINQ to support the sort of the notion of equality, except it's two expressions that equate to something that might be considered equal. You want to use the equal during or when you're doing joins. You don't use them in any other scenario. If you're actually just doing where something equals something, that equals is an equality operator. I'm going to project the result here to something that has a category property, and this would just be either say C, or I could just say P dot category, and the other one is a product name, and its value is P dot name. Now we did cover anonymous types in the previous session in part 1. Just as a refresher, the anonymous type, this is an anonymous type now, cannot be sent out of the methods or can't be sent into methods as parameters. They're anonymous, so you can never reference the actual type. You can reference the instance, but you can't reference the type itself. So you can't define a signature that takes in an anonymous method or returns an anonymous method. You can have your own specialized type. Instead of newing up an anonymous type, you could new up one of your own types that has whatever properties you want, and you can assign them from the query results. And the other thing is, I could just instead of saying P dot category, or I could, instead of saying category equals P dot category, I could just remove this part, because it implies then that the name of the property is category. We have not actually specified the name of the property, so that's something people don't recognize or don't know of for the most part. So I didn't have to define the property category equals P dot category. It will take on this name. Similarly, if I wanted this to be just the name, I could have just left this alone and just done that. So this would be an anonymous type that has two properties, a category property and a name property. Of course, then I'll have to change that here to be name as well, so that it would work. So let's see the result of this operation here. So we see there's a bunch of beverages here, 3 beverages in fact, and the way the data is laid out is they're kind of all grouped together. That's because of the join itself. So this is pretty simple. It makes sense for most people to understand what a join is. What if there were scenarios where some data was, so let's say the left hand side table in this case did not have beverages. What would happen? Now as joins go, we shouldn't see any data for beverages, as you can see here. Sorry about that. So there's no beverages, starts with vegetables. So beverages don't exist anymore because of the fact that the left table in this case, our categories table, does not contain beverages. Conversely, the category table contains canned as a beverage, but there are no products that are canned. So we're not seeing canned. We didn't know that we were missing it. But in fact, there's no line item, if you will, for canned. So this is the full set of products with their beverages, with their categories, but there's no canned here. So it's meat, seafood, dairy, vegetables, beverages, but no canned. So that's a left and inner join or equijoin. That's how you would write the code for it in LINQ. The next one we're going to be looking at is group join. So group join is very similar. It's not something that's available to us in in SQL directly, and you'll see why that is. It's very similar in syntax. If I look at the 2 syntaxes here, they're very similar here. The difference is that this one is doing a grouping, so it's putting the result into something we call here PS, which is missing in the join part. And then when we select, we're saying again category equals C, products is equal to PS. So all of the products that belong to a specific category are in PS. And we can then take the PS, and so this is like a many, as in there's many products. That's why I call this property products. And what happens is then, because of the group joining, even in grouping is the same concept, you have to then use a nested loop to extract the information out. So for every one category that could have multiple products, is how you're going to see it appear over here. So let's call this method. So syntax wise it's similar to inner join, but it's just got the additional into PS in this case, or into is putting the result into some other variable, and then we can reference that variable later. And what I've done is I've indented the products with the tab. So when you see the result, put a breakpoint there. So let me put a breakpoint. Okay. So let's scroll up here a bit. So you can see here that there's sort of one record, if you will, for beverages, and then repetitions for the products that make up that or are part of that category. Similarly, one record, if you will, for vegetables, and then all of the products that are part of that category. So this is actually very much like how we would like to see data when we get data back from our databases, because invariably that's what we're trying to do. We're trying to display this data not as a denormalized record set, but more as a normalized record set. So this kind of converts the joined result, if you will, back into a normalized form rather than a denormalized form. Now you could do the same thing without doing a group join. You could just do a lookup. So let me do it here. So I'm going to define a lookup here, and I'm going to say result, which is the result that we see over there. So the result of the join. So result dot toLookup, and this toLookup takes in the key selector. It's kind of like your select statement, right? It takes in a key selector, gives you the in this case the category that's coming in. So I could just do, C goes to C dot, I shouldn't use C, I should probably like use P just so it's easier. It's not C dot category but P dot category. Doesn't make a difference to the actual function, but it's more legible, I think. So if I look at this, the lookup now, should see kind of the same. Oh, didn't. Oh, actually, didn't want to do that. I just didn't want to print it out. So if I look at this here, oops, what's happening with my mouse? I don't know why it's flickering like that. Okay, there you go. And then for the key, we have beverages, as you can see here on the right hand side. And when I expand the result view, I'll see all of those products that have the beverage as a category. So it's a one-to-many, right? The key being the sort of the outer, and the nesting being the products in this case that make up the key, which is the category. So you could achieve the same result by just doing a to lookup on the join, but it's a little extra work or one more step to do. So I prefer, if I need it, just to do this. It's simpler, plus it gives you the ability to project some things the way you would like it, rather than having to deal with trying to project it in a join itself. Not in a join, but in a join. Okay, so that takes care of the group join and inner join. Let's look at now the left outer join. The left outer join is, of course, it's a left outer join in terms of how we understand it to be in a database. But let's look at again just the difference between the two syntaxes here. So now the difference between the group join and the left outer join. So far, if you look at these two lines of code, they're pretty much the same. The difference is in this third from, which is like it's almost like a join on itself, if you will. So from P in, PS at default of if empty, and the reason is that when we have scenarios where the left table has, in this case, a category, but there are no products. So in our earlier case, the canned category did not contain any products in the products table. Then we don't see can, but the left outer join is essentially saying I want to see it. I want to see the record, irrespective of whether there's a product for that category or not. And so we define this. We use the from P in PS default of empty, and essentially what it does is either gives you the default value or an actual existing value if it's not. Default in our case is null, because the P is a reference type, so it'll be null. So when we do a select, what we got here is for product name we have a conditional. We're saying, well, if P is null, then give me product, no product, otherwise give me the name of the product. And if we run this thing, we'll see what the output is. So the sort of thing to notice here is that the canned products, which doesn't have any product on it, is now showing up here in our result, which was not doing so when we were doing the inner join. Let's look at something else. Let's say if we had beverages that was not here in the left-hand side table, then that should not make any difference to, there's not to be any special treatment, if you will, for the fact that the left-hand side does not contain any data, because the left outer join says, give me everything from the left and all matching records, if you will, on the right. And if there's no matching record, then in our case, we're still putting the no product here. So that's not changing for the left outer join. There's another way to do this left outer join concept. Instead of using default of empty, this default of empty has actually an overload that gives you, in this case, it knows the type, so it says give me the default value for product. So we could actually just do new product and give it a name of let's say none, just to keep it different, right? And then over here we didn't have to do this. We could just say p.name, because it would give you back a new product if it's, so the default now becomes a not a null but a special kind of default, in this case a product that has a name called none. And if I run this now, you'd see that instead of can being no product, you're seeing can now showing up as none. So that's one use of the default if empty. but that's also how you do a left outer join. Very similar, all three of them, join, group join, and left outer join, are pretty similar. Okay, so we're done with that. Next up is the LINQ random number generator. So let's look at that here. Generators. Okay. So I have these methods. I've predefined the method, but there's no implementation. So we're going to implement them here. So the first one I want to do is I want to generate, write a method that generates a random number or random numbers. If I give it 20 in this case, so the number of elements, it should return to me a sequence of 20 random numbers. So I'm going to start off the first one so that there's no, you know where I'm headed with this. So in uniworld.range, 0 to number of elements, depending on whether it's inclusive or exclusive, we're not defining that, but let's say from 0 through, if I want number of elements to be 20, then it should return to me 20. So what I have is now in range of numbers going from 0 through 20. I'm actually in this case just going to remove the -1 because in my mind it's number of elements. So maybe, yeah, actually I'm confused. I don't know what it really works out to, but nonetheless. Now what we want to do is we want to take these numbers and we kind of want to randomize them. So now in SQL, I don't know if anyone has done this, but in SQL you could just say order by random. Random being a function in SQL, at least in SQL Server, Microsoft SQL Server. So what I've done is I have a random class that I've already instantiated here. And what I can do here is I can do order by. Now in order by, it takes in a key, but we're not going to use the key. In this case, we don't care for the number, which is one of these numbers here, right? We're not interested in the number. What we want to do is we want to order this by random.next. I'll explain this. What's happening here is pretty cool concept. Whatever the number is, I'm not interested. What I'm saying is whatever it is, just order it randomly. So get the next random number and then use that random number to determine the sequence or determine the ordering. But because they're coming in as random, the ordering itself will be random. So that's how this one works. So let's look at the net result of this. Let me set this as the default application. Okay. So when I run this, I'll see that there are 20 random numbers. I've listed them out horizontally like this with the space in between them. So that's 11 and that's 12 and 2 and 18 and so on. So that's random. So they're numbers from 0 through 20, but they're showing up in a random sequence or random order, right? Okay. So the next one I want to do here is now instead of being limited to 0 through the number of elements I want to be determining my own range of numbers. So I want to define a minimum and a maximum, and then I want to determine the set of number of elements here. So I'm going to start off with the original, the previous code here, and the number of elements is the same, but I'm going to have to change this part here. So what do you think we're going to do here? So this is where sort of the mind bending starts to happen, where you think, oh, okay, you thought you understood how LINQ works under the hood or internally, but it's when you start doing stuff like this, where you really understand how things are working under the hood, what it really means when you have some methods or overloads, and how to use those things, how you can use this. So here, what I'm going to do is I'm going to select, and when I select, again, I get the number that. If you want to see the signature here, you can see that the signature I'm using is the one with func int and t-resolve. In this case, our t-resolve would be an int as well in our case, but we're essentially implementing the selector. So what I want to select, obviously I can't use this number or the number that's in the uniworld.range because that's not going to be between min and max. It's just going to be from 0 through some number. So I want to use, now random luckily has another overload for next that takes in min and max values. So it takes in two parameters, min value and max value. So that totally helps us here, because we can just say min comma max, and that's the end of that. So once again, we're ignoring the number that's coming in from our range here. And what we're saying is, by the way, when I want you to select, I don't want you to select that n. I'm just ignoring that. I want you to select the next random number that is within the range of min and max. And so that gets us what we want. So I could call this method now, let's say from 1980 through to, let's say, 2050. The year, in this case, I'm seeing as 2050, and I want 20 of these numbers, 20 years in a random fashion between 1980 and 2050. So you're seeing now the range of numbers is not limited from 0 through the number, in this case 20, but they're ranging from the year 1980 through till 2050, right? So again, they're random. They're random because of the fact that I'm selecting the random number which is being generated. In this case, I'm ignoring the actual number. I'm just selecting the next random number within the range. Okay, so far this looks pretty cool. We're going to shift slightly from instead of being random numbers to a string that is comprised of random letters. Okay, so it's a slightly different concept here. So I'm going to start off with what we had previously in the previous things. So one of the things that was not apparent here was that we are using the range as a loop counter. So we're iterating over this loop, if you will, n number of times. But for every time we get to an iteration, we are selecting a random number. So in this scenario, this range was being used as the loop counter, whereas in this case, the range was actually being used as the values themselves, right? So we're going to use the range here again for char length. So if you say you wanted a unique ID, that's 20 characters long, I'm going to use this enumerable range as the loop counter. But again, what am I going to be selecting? I want to select not numbers, but I want to select characters, letters, and I want them randomly. So slight difference is that we know that the range of letters for A through Z capital is what is it? I think it was 65 through 90. That's A through Z all uppercase. So get me a number between 65 and 90. Convert that number to a char. Return that the number, sorry, the character out here. So let's assign this to something called chars. But we need a string coming out of here. So then we'll return a new string that takes in the chars dot to. Now chars is an enumerable, whereas the string constructor takes in an array of chars. So that takes care of that. Now if you would look at this, I can call this get unique ID. Ignore that and ignore this. And this get unique ID, let's say we want 20 characters, right? Unique. Okay. So what we have is a unique ID that's comprised of only uppercase letters in a random sequence. So that's good. Now let's look at up the ante a bit. What we want to do is, rather than being limited to just the uppercase letters, in this case A through Z, we want to have this full set. So we have numbers 0 through 9, alpha uppercase letters A through Z, and lowercase letters A through Z, and that is our kind of the set of digits or numbers, sorry, alphanumeric items we want to make a random unique number from. So I want to essentially call get unique ID 2, But instead of being limited to just A through Z uppercase, we want to, so I'm going to just copy this. Here. And this is now length. I should probably just have the same. But rather than doing this, we do what? So we know we want the characters to be randomly picked from this array, right? So what we want is ID chars of something random, right? So what we want is ID chars of a random number. So random.next. But the min and the max has to be within the range of ID chars. That is ID chars dot length -1, right? So only then would this be valid. And that ID chars, the index, if you will, inside of ID chars. So this is a random index within the ID chars array. And then we convert that chars into an array and return it. So that should be just like the other, except the difference is that we're going to see alpha, numeric, uppercase, lowercase, right? So we see 592. We also see a lowercase a, x, etc., and we see some uppercase letters here as well. So I hope that we found this interesting, because I do. This definitely bends my mind a bit to think about different ways in which I can use LINQ generators. So now let's go back to my slides and make sure we're covering the things I had planned to do here. So we've finished this part. We've done the LINQ, the group join, outer join, etc., and LINQ generators. We just finished that. Finished with the demo. That's good. And now we go to iterators. So just once again, iterators are have been introduced The iterator language feature was introduced in .NET 2, but iterators have existed in .NET and C# since the very beginning. So is the for each, for that matter. So what we want to look at now in our classes is to support this aspect. So let's see what I mean by that. So we have LINQ support for custom classes here. Now I have two classes. This a president class, which is just got a few properties here: ID, first name, last name, year, email, and is alive. And then we have a presidents class, which is in its constructor for now is just holding a collection of presidents. But what we want to do is we want to be able to use this class directly without exposing the internal collection. I want to use the class directly in a for each, for example. So let me show you what that means, what I mean by that. So I've got an instance of this. I want to be able to do something like this. I want to be able to do for each var item in presses, and then I want to be able to do that item. Okay. Now what it's saying here is that does not contain, so let me okay, there it says it does not contain a public definition for get enumerator. But actually, for those who don't know, in order for your class to support for each, it needs to have just two things. It needs to have a method called moveNext, and it needs to have a property called current. And if the class has these two things, meaning the moveNext property method that returns a bool and the current that returns the current instance, the for each actually works. But the compiler is giving you this error that's saying you don't implement, or this class president does not implement doesn't have a method called get enumerator. The get enumerator actually is one of the methods, or is part of the IEnumerable interface. So what we have to do is implement IEnumerable interface in our class here, in the president's class. So IEnumerable, in this case, of president, singular, right? When we implement this class, we see that there are two methods that need to be implemented. Now both are the same. They both are returning an IEnumerable numerator, of president. This is just the explicitly implemented interface, the old style, the non-typed or non-strongly typed enumerator. So it returns an object and you have to still cast it back. So this is the old holdover from .NET 1.0 before generics, but it is also the explicitly implemented interface. So how do we go about doing this? How do we get a get enumerator? Well, if you look at enumerator itself, it has got this one method called get current here, and IEnumerator, the older hold-off, has got what we need to implement, the current and move next and reset. So I'm going to show you in this demo here how we would go about. I think it's important to understand because there's lots of compiler magic going on these days, and people don't. At least I don't understand things when there's a lot of magic. I need to understand what's happening under the hood first, and then I can kind of live with the magic, if you will. So what we want to do here is implement the IEnumerator by hand, if you will. What we used to do in .NET 1.0 and 1.1. Okay, so the way we were sort of asked to implement this was with the help of a nested class. I'm going to call this precedence iterator that implements IEnumerator of precedent. Okay, and this precedence iterator has all this stuff you have to implement here. Now it looks a bit scary, but it's actually not so bad. I'm going to add a constructor here, and in this constructor I'm going to take in an array of precedent. So an array of precedents. Let's call this source. I'll define a private an array here also called source, and then in the constructor I'll just assign the source to equal the source that we were sent in. And the reason is within this nested class I want to have access to this private member of the outer class here, precedence. So when I create the instance of the nested class, I'll hand it this collection, and then we'll be able to use that within this nested class here. Now another thing we're going to need here is an index. Let me just show you what happens is, so this move next method essentially is called by the for each, and it says move next, like get next one, not get me the next one, but can you move next, because it returns a bool. And if you can, you return true. If you can't, you return false. So the for each knows to stop. And once it's done the moving to the next, it asks for the current. So in our case, the current is going to have to be, let's say, return source of some index. So let's call this current index, which we don't have yet, but I want to explain that in the concepts. We need to return the current index. So I'm going to define this current index here as a private member, which is of type int. I'm going to set it to -1 initially, because what happens is the for each calls move next first and then calls current. It doesn't call current as the first thing. It calls move next first. And so move next means we have to be able to increment it, and we want to give the first item in the collection. So rather than doing math later on or doing -1 later on, I'm setting it to -1 up front. So it moves next first, which makes it 0, and then when I say get current of 0, it actually works. Okay, and we can use the same implementation here. Once again, this is the explicit implementation for current. We have the generic, so the strongly typed version of current over here has the same implementation. So they both have the same implementation. You can imagine reset to be nothing but setting current index to -1 again, because that's how you would reset it. Now in C#, nothing ever calls reset. It's not, the for each doesn't never calls it, and certainly anything that I know of in C# has never used reset. So it's not like you have to actually implement it. So we got that. The dispose, because of IEnumerator implementing dispose, this class is disposable, if you will, just by the virtue of the fact that the IEnumerator also implements iDisposable, and so this class also is disposable, but we don't have to do anything here since we don't have anything to actually dispose of, but it's there. And the for each, in fact, is going to be disposing of this class once it's done, because it implements iDisposable. That's a compiler implementation. So all we left with now is this guy here, and what we're saying in this method, as I said earlier, was if you can move next, means if your current index has not reached the length of the source in this case, then return true. If not, return false. So we'll return here current index is less than or equal to source dot length -1. This is the pre-increment operator, slightly different from the typical post-increment operator. Again, we discussed this in the previous part 1. But the pre-increment basically says first increment and then give me the value. So by the time it does the comparison here, the value has been incremented before it actually compares. If it did this as current index ++, then it would first give me the value as is, do the comparison, and then increment it after the fact. So we want here to be a pre-increment, not a post-increment. Just makes our lives a little easier, the code to read a little easier. Okay, so that's the complete implementation for this inner president's iterator class. And what we do here now is return a new president iterator class, giving it the president's collection that we have in this outer class. But rather than doing this, I would need to copy the same thing in both places. I would define a private method that returns the enumerator of president. Let's call it get numerator internal, and it actually has this implementation, and then these guys can both just call the private method, right? So that's that. So that's it. Now once we've done this, if I went back to our for each, it's just fine. It's happy. It's not complaining anymore. And if I were to make this as the startup project and run it, we'd see that it is printing out all our presidents from 44 through till 35. So that's let's see if that's the right number. It probably is, and if it's not, it's a matter of changing around the -1, but yeah, 44 to 35, so that's correct. So the for each works. Okay, so that's the iterator. Now that was how we did things in .NET 1.0. What about since .NET 2.0? Well, the compiler does a whole lot of work for us in .NET 2.0, but whatever it does, it boils it back down, or it essentially generates the code that does all of this. And this is nothing but a state machine. This is essentially saying, move next current, and the state machine, by the help of this current index member here, is maintaining the state of where are you at this moment in time. So it maintains the state of where you're at, and so this is called a state machine. It implements this in nested class automatically for us, but it made our lives easier. So I'm going to delete this class. Okay, so there, all the hard work we just put in, gone. And therefore we can't use this. But what we can use is this. What we do is presidents, and here we have introduced a keyword, yield return item. This is now called an iterator block. This is the new feature that was introduced in .NET or C# 2 called iterators, and all it is this thing, yield. And this yield and return essentially re-implements everything, all the code that we made earlier, that we wrote earlier, the nested class, essentially translates this to that, and everything just works as it is. So both of these implementations are correct. Of course, who wouldn't love the new implementation? But how does this actually work? It's not very clear what yield return does to for most people, and I certainly was pretty amazed when I first saw this behavior. So I'm going to step through some things. I'm going to put a breakpoint at the point of entering this method, then a breakpoint in every iteration here, and a breakpoint at the end of this iteration here. Let's see how that goes. And even though the for each is essentially calling the get enumerator method here, we know that behind the scenes it's going to call this. It's going to reach here eventually. So let's run this application, and it's going to come and stop here. So it's come and stopped here for the first time, right? I'm going to step, 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 yield return. When it hits the yield return, it's going to leave this method because it is a return, except it's not a return, the full-blown return, it's a yield return. So it yields to the calling application, the calling method. So let's step. I'm not jumping out of this, I'm stepping into it. You can see here my mouse, I'm stepping. So step, it comes out. It's gone back out to the calling application. This is pretty weird if you think about it. How the heck did it do that? And why is it doing that? And we continue on stepping here. It's now got the very first item, and it's consuming this first item. So as soon as it got that first item, the other method, yield, returned to the calling method. The calling method was able to consume this first item as soon as it came out. And then what? So here's the fun. You come back in to get the next item in the for each, and it comes back. It didn't come back here. It didn't come back here. It didn't even come back here. It came in where it left off, which is over here. So it left the method over here, and then it came back where it kind of left off. So it remembers where it left off. Now this is a debugger doing this magic in terms of showing us how I think we would like to see things working in terms of in our mind. We'll wrap around how iterators work, but behind the scenes it's using that state machine. So the state machine is still in play. The compiler generated that state machine, but the debugger is showing us this kind of convenience of debugging and making us understand how things are actually working. So it looks like it's re-entrant code, but it's not really re-entrant. It's just using the state machine behind the scenes. But it's interesting to see even the behavior here is pretty weird, because iterator blocks, as I said, are the sort of the foundation for deferred execution in LINQ, as well as for streaming in LINQ. Because as you're seeing here is, as soon as an item is available, we return it. And the consuming application or code is able to consume it. If that was being sent one chain higher or one step to an outer method, it would go out to the outer method and so on. So as soon as the inner method has available to the item, it sends it out to the calling method, that sends it out to the calling method and so on. And that's streaming, or that's also the reason that deferred execution actually even works. So I'm going to step here again, just so you can see a second round of this whole thing. So I'm going to step, 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 yield return, and it jumps back out, comes here, continue on as if it was just iterating over here, consumes the second item. When it comes back in for the third item, it goes back to the calling method and says, okay, now give me the third item. So it's come back again where it left off and so on. So that's how iterators work. And it's a pretty interesting concept, but I don't think a lot of people understand really how this stuff works. So I thought I'd show it here. So we've done a few things. We've implemented the old style iterator, then we implemented the new style iterator in our class, the custom class, and we are now able to use this custom class with the for each, which is exactly what we wanted. So notice we haven't exposed the internal property, but we just converted our class, our custom class, to be iterable, if you will, using implementing the IEnumerable interface. And just let's go back in here. So all we've done is we've done this. We implemented the IEnumerable interface for president in this case, and then we've used the iterator block to implement it. That's it. Okay, so that's how simple it is. The next thing I want to show you is we've done for each. Actually, I can do the get enumerator here as well while we're at it. So behind the scenes, what might not be common knowledge to people is that behind the scenes, the compiler rewrites this code into different kind of code, and the code looks something like this. It's using, and what it uses is, so let's call this enumerator, and we say presses, which is the instance of our class here, dot get enumerator. It calls get enumerator, but remember, get enumerator returns to you an disposable, which is why we're using it in the using here, and that's what the compiler generates as well. So essentially, this enumerator is disposed of, and inside of here, while enumerator dot move next, which is bool returning. So if we can move next, in our case, we're writing it out. Enumerator dot current, and that's it. So that's what the for each translates to, or is translated by the compiler. Just before compiling it, it converts it over to this, and then this thing works as it is. So whenever you see a get enumerator method on a class, you can assume it can be used in a for each, or you can use it like this if that's what you want. Either way works. I think for each is obviously a lot more convenient. Okay, so we've taken care of get enumerator as well. So now we're left with where and select. Now, because this is implementing IEnumerable, we should be able to directly use it in like a LINQ statement. So let's try that. So presses dot okay, so I did this before. So if this LINQ namespace was in here, we'd see all the extension methods on IEnumerable, and so we'd see let's say where, right? Now the where has a signature that returns an IEnumerable. It's an extension method that returns an IEnumerable of whatever the source is, and it takes in a method parameter which is of type func that takes in a source in bool. This is the second overload. So let me okay, this one is the first overload here. Oops. So it takes in this case, it takes in a func bool, and they call out a predicate. The predicate is nothing but a function that returns a true or a false. So not that that makes it a predicate, but the variable name is a predicate. So our next sort of exercise here is to, what if we want to implement the sort of LINQ methods, if you will, on our own classes. So now this where is not supported, and what I would also like to do, rather than just doing this, I want to be able to say something like let's say alive from P in presses where P dot is alive. It's not going to help me here, but what I'm trying to do is do that. P dot is alive, which is a property on our president class, if you remember, or if you probably don't, but that's what it is alive. So I want all the presidents that are alive. Select P. Okay. So it's not helping me, as it's not recognizing all of the stuff here. So it's not supposed to be while, it's supposed to be a where. Okay, so where P dot is alive. So it doesn't like this, of course, because it doesn't know what the where is. So it says this method where has not been found on this class. And are you missing a LINQ system or LINQ directive? And we are intentionally leaving that out. We want to implement our where clause ourselves, the where method ourselves. So how do we do that? So going back to our president's class here, let me remove all this. I'm going to first define the signature itself. So this is a public method that returns an IEnumerable of president, and we're going to call it where, and it takes in a func of president bool, and we're just going to call it predicate, just as simple and easy to remember. The implementation. Now this is actually a higher order function, meaning it takes in another function as a parameter, right? It's a higher order function. And the way we're going to implement this is simply by iterating over our president's internal collection, and we call the predicate. So if predicate, giving it the item, yield return item. And as you can see, because of this yield return again, the where is a deferred execution. As in, it's only when you start to iterate over it does it actually function. And we can put some breakpoints in here, just so we can see this functioning like we did earlier. Okay, and in here now the error has gone away. This actually is going to work. So all we've done is we implemented the where, and this thing is going to work. Now we have some presidents here that are still alive, like Obama, Bush, Clinton, Bush Senior, Jimmy Carter, and so on. So they're all, some of them are alive still. Let's look at this function here of work. So I'm going to change this to alive. Okay, so it's only when we hit this part here does the thing, because of the deferred execution, does it actually start to iterate over anything. So we come in here, and now I step, and when I get to alive, at that point it hits our where method and comes in here. At this point we actually have an item, and we see it's alive is true. So when I step in here, the predicate succeeds and yield returns this specific item. In this case is Barack Obama. go back in here, it now gets the item, consumes it, and then goes back to get the next one, hits just where it left off. So it left off here, it's come back in here, and that's how it continues on. The next item and so on. So again, item succeeds, or the predicate succeeds, and so on. So this is the implementation of a where using iterator blocks again, and as a result of which, again, the where clause is a deferred execution. Okay, now how come the select is working? Even though I have the select here, we won't be actually implementing select, but I want to just show you or talk about it. So this, because I'm not projecting it, I'm returning the P as is. I'm not projecting it. I don't need to actually implement select. If I were to project it in some other form, so let's say name equals P dot first name. It's not going to help me. Plus P dot last name. If I was to project it like this, then it was going to complain about this guy here, which says there's no select method on the president's class, and then you implement select and so on. So it's, of course, one more question: why would we do this? Of course, I don't expect you to actually implement this yourselves, but just wanted to show you some of the underpinnings of what's going on under the hood. So most of the methods are pretty trivial. There are a few non-trivial methods, but most of them is just busy work. Some methods have 20 overloads, 15 overloads, so you're doing a lot of work. But there may be some scenarios where you don't want the full functionality of LINQ. You want to just have like a where, that's all you care for, is allowing for filtering while allowing somebody else to determine the criteria for filtering. So we'll be looking more at these higher order functions and other uses for them in our next part. So that takes care of this whole section here on supporting LINQ and the for each support. So let's move this back to P. Okay, everything's back to where it works. So next up is delegates. So I'm going to go to our project here. Might as well make this the default project or starter project. Okay. On to delegates. This is how you define a delegate. Delegate is defined like this. And in this case, this is the type. It's not the name of the delegate, it's the type of the delegate. Just like you would have a class. That's not the name of the class, that's the type, or the type name. So this is the type name of the delegate. And what it's saying here is that this is a delegate that returns a void, takes in a parameter of type string. The names are irrelevant. This could be called anything. It doesn't matter. But it's the types. So this delegate takes in a string and returns nothing. But what is a delegate? Maybe I should just introduce that concept to you earlier. And I have a slide that I talk to this about. So why not just look at the slide here. So the point here is to give you a deeper understanding of delegates, lambdas, and anonymous methods, and also to help you read some of the code completion, parameter completions that you see typically when you're using LINQ. It gets very, very hairy looking and confusing with all those angle brackets, and I think that certainly when I first looked at this stuff myself, it was like, I have no idea what am I seeing here? Like, how do I even decipher or read this syntax? And so in this session, this last part of this part 2, I want to kind of give you a better understanding of delegates, anonymous methods, lambdas, and help you understand how to decipher or read the syntax and what it all means. So you kind of remove all of the scary parts and distill it down to very simple concepts, so you can then use those concepts in your own applications and classes. So that's what we want to do with delegates. And a delegate is similar to, if anyone's from the C++, C, Delphi backgrounds, very similar to a method pointer or a function pointer, but they're type safe. So the difference is that a method pointer or a function pointer, sure, there's a pointer somewhere in memory location, and if you happen to know for yourself that it happens to be a method pointer or a pointer to a method, but there's nothing that tells you anything about the signature of that method. So in other words, you could call it with all kinds of things, and you don't even know what it's going to return. And you're going to have a runtime exception because you don't know necessarily how to call the method. There's no information in that pointer that tells you about the signature of that method. Delegates are slightly different. Delegates are strongly typed or type safe ways to call methods. They do delegate in the sense that they call another method, the method that they're delegating to, but they themselves are strongly typed. That makes the compiler can then check you at the time of compiling to make sure you're calling those delegates with the right signature. So that's the big difference between delegates and method pointers or function pointers. Delegates allow you to then send methods or code blocks to other methods. So that's the higher order function capability, where of course you have to think in that way. You have to get a sense of how to think about defining your own higher order functions, which we'll be looking at in the next part 3. But essentially the delegates are the basis for that. Delegates are also, some people call them callbacks. Of course, callbacks are another methods. They're not necessarily a delegate, but the concepts being the same. And in C#, so in C# 1.0, there were two kinds of delegates. There were single cast delegates and multicast delegates. And in .NET 1.1, they decided to kind of the class still exists, the single cast or the delegate class still exists, but they decided to descend all the delegates from multicast. And we'll look at what multicast means briefly in the code examples that we look at. So let's move back to code. So as I said, this is the compiler behind the scenes converts this to a class that descends from multicast delegate. And that's, it kind of rewrites this code at the time of just before compiling to define a class definition that has this class name that descends from multicast delegate. And the multicast delegate has a few properties that we'll look at shortly. Just keep that in mind. A delegate is nothing but behind the scenes it converts to a class. So we could have different kinds of delegates defined, right? This is just one type transform delegate in here. So I want to have a variable of type transform delegate. I'm going to call it A, another one B, another one C, and another one D. This is just a shorthand way of defining multiple parameters, multiple variables that are of the same type. So if you haven't used this, don't use it in your code. I don't normally use this in production code, but it's nice to look at. It's short when you have to type it yourselves, especially for demo purposes. Let me define, I want to define a method that has this signature, right? So this method takes in or returns a void. Let's call this the name of this method, method 1. And it takes in a string as a parameter. It doesn't have to be called data. The parameter name does not have to be called data, but I'm calling it data. And in here is what it's going to do is it's going to type in data method 1. Okay. And then we have another method that has the same signature. And we're going to call this method 2 and method 2 here. So both these methods have the same exact signature as this delegate here. We have variables defined of this type, but now let's see if we can define some instance or assign an instance of this delegate to something. So I'm going to say A is equal to method 1. Now if you're confused with this, if you're not confused with this, I'll ask the question, why aren't you not confused with this? Because unless you've been using this often enough, you should be actually confused. But there's lots of magic going on behind the scenes. Let me explain that magic. So in .NET 1.10 and 1.1, what we had to do was we had to say A is equal to a new instance of transform delegate, and as a parameter, constructor parameter, and I'm certain you can't read this signature as well. I still can't read it. I have no idea what that even means, but what it's saying is I want the method you want me to delegate to as a parameter. So what I'm saying is I want to create a new instance of transform delegate, and I want to pass it in the method I want it to delegate to as this constructor parameter, so that when I call A, and A has got the, requires a, let's call this A as well. And if we run this, it's going to call this method A, but the A delegate delegates to method A, or method 1 here. So it should really execute this line of code, right? So that's where it's come. And if we run this, or we look at the output here, you will see that it says A, call method 1. Okay, so that's doing. But since .NET 2 or C# 2, the convenience of this was you could just do that. You didn't have to actually new up an instance of a delegate. Behind the scenes, the compiler rewrites the code back to the way it was in .NET 1.1. So this would have the same behavior. I'm going to remove that breakpoint. It'll have the same behavior as what we saw earlier. No change. Right? Okay. Now the delegates, as I said, have other properties. For example, a.method. A.method is nothing but the method that has been assigned to. In other words, the constructor parameter that it got assigned to the property method. So going back to this, if I had transform delegate method 1, then this instance method 1 here has been assigned to a.method. And then when you call this method, the compiler has written the code not to do a.method, but it's doing a.invoke. Invoke, sending it the parameters that you are expected to send in. So behind the scenes, the compiler is rewriting the code to be doing this, but we are seeing this as simplistic or convenient ways of calling a method, and we get the compiler, the parameter completion help here as well by the IDE. So we know that we are supposed to send in some data that's a type string. Okay. Hopefully that's explained my first part. So I'm going to go back to our simpler syntax. Hopefully that's not going to get confusing. So I'm going to say A is equal to method 1, B is equal to method 2. This is pretty much the same. C is equal to A plus B. We're not doing math here, we're just doing delegates. And because delegates are multicast, we are able to make this statement like this. What we're saying really is that C is going to call these two delegates, which in turn is going to call these two methods. When I call C, I should be calling, even though I just called C once, behind the scenes it calls method 1 and method 2. Let's look at that. So when I call C with C, like that, and I run this, you'll see that it called both the methods, right? Method 1 and method 2. So that's really what happened there. And I could then do D is equal to C minus A. Oh, C minus A. So what that means is, even though C is A plus B, D is now C minus A. In other words, D is just B, right? So if I was to call D here, I'd find that it only calls method 2 and not method 1 anymore, because the D delegate was C minus A, right? Okay, so that's the very high level understanding of what delegates are and how you would use them in your own code. Now let's look at something else, something similar. In .NET 2.0, they introduced the feature or concept of anonymous methods. And I'm going to explain some of this stuff with the help of LINQ. So I'm going to first have variable numbers. That is nothing but okay. And then I want to do something like numbers.where, and in where here we are seeing the syntax. So let me also explain the syntax here for those who haven't understood this. This is a func that takes in an int as an incoming parameter, and it returns a bool. Okay, it's a func, and the func is just the type. It's not didn't say anything. They've predefined these types in the base class library, so they're already there for us to use. I think that's probably one of the big confusions is that it expects a func, which is the predefined type. And in this case, the func takes in int as a parameter and returns a bool. And it's taking an int as a parameter in this case because what we're dealing with here is integers, right? So because this is integers, it sends us an int as a parameter, and we return true or false, determining with, do we want to use this as our result or not. Okay. If I were to define func myself, it would be something like this. So I'll first define the non-generic version, and in this case it'll be bool returning. Let's call it func mine. I could call it func, but there'll be conflicting names. I'll just call it func mine, and it takes in our case, in this specific case, it takes an integer, right? So num. This is the signature, a method that takes in an integer and returns a bool. The generic version of this would be defined as delegate t result, because we don't know what the result is. It could be anything, and it's let's say func mine 2, and it takes in something. So it takes in one arg, so let's call it t1, and returns t result. So this t1 here, let's call it arg1. I don't know what they call it, but that's the definition. That's how you would define a func. Of course, if this was not mine 2, this is how it would be. So the func that we're dealing with in the where clause currently is sort of defined like this. Now there are many funcs, as I said earlier, that have been predefined by the runtime or by the base class library. So if I was to look at it over here, I'd say func. Let me see, I can zoom in here. Oops, sorry, I didn't want this zoom, I wanted this zoom. Okay. So when I do a func here, you can see there's T1, T2, T3, and there's 17 overloads. So there's all these multiple T1, T2, T3, and so on up to 16. So 16 incoming parameters and one outgoing parameter. So these are the sort of predefined in the base class library. Okay, I hope that explains something here, but we want to look at some other stuff here now. So in the where, I need to give it a method or a delegate that has the signature, a signature that takes in an integer, returns a bool. So what you could do is, let's define this method. Let's define a method that returns a bool. Let's call it my predicate, and in this case it takes in an int as a parameter. And let's say I want to return in this predicate, I want to return all even numbers. So I'll just say return num mod 2 equals 0, right? That's the implementation. Now what we're used to doing in LINQ is we kind of do it in lines. So we say n goes to n mod 2 equals 0, right? But what we could also do is give it the name of the method or a delegate. So give it a delegate. And now this will work in the same fashion. Of course, we can have multiple methods like this in the same signature defined with different implementations, and we could decide which one to use where. The lambdas are kind of convenient. But I want to show you what you would do with just delegates. So lambdas are delegates. And this is sort of the old style of doing it, where you might, it's not necessarily old style. If you're repeating the same thing over and over in your application, you might as well have a method that you can reuse without having to repeat this implementation over and over. It also kind of cleans up your code a little bit, because you can you're not cluttered with the lambdas and the angle brackets. So this is one way to do it. In .NET 2.0, they introduced what they called anonymous methods. And anonymous methods go like this. You say delegate, and in this case say int num goes to, and here you could say return num mod 2 equals 0. Okay. So this is not a lambda, this is just a delegate. So this looks like a regular method, right? It's got, instead of a name, it's got the word delegate. It's got the set of parameters here with the types, and it's got the open close curly within which we have the entire implementation of this method. So barring the name and static and this bool, so basically this part here is the same as what we have here. That's a delegate. This is an anonymous method. Anonymous methods can't be, they're anonymous as in they don't have a name. they can be referenced by the instance of the delegate, but they can't be referenced by name. You can't call that method using a name like we can do with myPredicate. We can't say, hey, call myPredicate. That's not possible. They are anonymous. But once we have a reference to the delegate, we can actually use it or reuse it. So we could define something like this. We could say, okay, here's I have a func int bool, which is the signature we're looking for. I'm going to call it mydel, and I'm just going to copy this over. So that is a, oops, this is a delegate that has been defined. Mydel is now an instance of that. So that's like saying new delegate, etc., but with the implementation. So this mydel is now an instance of a delegate that has the same signature and has this implementation. And I could now take this mydel and just put it and give it to the where. So I can, even though this is an anonymous method, I can't reference it by name, but once I have an instance of it, I can actually call it. I can directly call it. I can call it mydel, and then of course what it takes is an int arg. It's going to return a true or false. So I could, give it 6. In this case, it's going to return to, a true to me because 6 is an even number. I know the implementation here is checking to see if it's an even number. So this result will equate to true. Of course, in the where, it's iterating over all the numbers, and so you see the result of numbers. If you want to see that, let's just so result will now contain all of the even numbers, and in this case the even numbers, oops, sorry, it's can't see my mouse clearly. Okay, so there's the even numbers, 2, 4, and 6. Okay, so what we've done is we've taken the anonymous method, we defined it as a variable, and we can now reuse the variable. We can reuse it here, we can call it by ourselves, etc. So it's anonymous, it has no name, but once we have an instance, we can actually call it. Now the transformation that took place between the old style, method with some of the verbosity here, static, bool, the name, right? The anonymous methods took away some of the sort of the cruff, if you will, where name disappeared, and we had delegate here, and then we had the type and implementation, but this part disappeared pretty much, and instead of the name we just have delegate, right? So the anonymous methods gave us some sort of help with regards to the amount of typing we had to do in .NET 2.0. In .NET 3.0, because of the way LINQ uses delegates a lot, they had to come up with we didn't want to see this code. I mean, we certainly don't want to be seeing code like this over here every time we did this, some sort of a LINQ statement. It would be pretty cumbersome. So they had to come up with a more succinct fashion of writing delegates, either anonymous methods or delegates. They're both the same. Actually, anonymous methods, delegates, and lambdas are all exactly the same. Some people I know, when I've talked to them in the past, say, oh, are they really? But they're the same. And what I want to show you is now the transformation that takes place from anonymous methods to lambdas. So here's what happens. If anonymous methods took away some of the cruff from the standard methods, lambdas go one step further. So in the lambdas, they said, well, okay, what is it? We are expecting a method here anyways, or a delegate here anyways. So do we have to specify delegate? No, we can take that out. Cool. Okay, that's great. And then if we take that out, we can't tell the difference between when the method starts and ends, and so we add a goes to new symbol. And this is also This is a Lambda statement block. It's not a Lambda expression, it's a Lambda statement block. It's all valid syntax so far. And then one step further from this is, well, what if for the most time you just want these one-liners? Why go through all of this mess, right? Can we not just take away the curlies? We can determine if the method returns something or does not return something, so we don't have to keep mentioning return. And it's a one-liner, so we don't need the semicolon, and then we don't need the close curly. And this is a Lambda expression. Again, it's all valid so far. You see there's no squigglies here. They went one step further and they said, well, when there's only one parameter, or even if there's one parameter, do we need the type? Well, you can just leave the type out. We know what the type is. If the first type, we know what the signature is supposed to be, so we can determine or infer the type. And we don't need the parentheses here either, so let's take the parentheses out, because we can determine the fact that anything in here before the goes to is a set of parameters. And this is now the sort of the Lambda expression that we're used to seeing. The only time you actually do need parentheses, is when you have no parameters. So when there's no parameters in a method, you need to put in open close parentheses. Of course, this method does expect parentheses, so it's parameters, so it's complaining about the fact that there's nothing that takes 0 arguments. But I was just going to show you here. So the time that you do need parameters is when you don't have any, parentheses is when you don't have any parameters. So for the compiler to be able to parse this code out, it's okay, if you don't give me open close paren, I don't know what you're really saying. But when you do have one parameter, then you don't need to do this. Now, if you have two parameters, you need to put the parentheses again. So you need to put the open close paren around two parameters or no parameters. But you don't need to do it for single parameters. So this is also valid in terms of syntax for lambdas. So once again, lambdas went from, delegates, actual full-blown methods, went to anonymous types, went to lambdas. Right, so the transformation. Now you can have defined lambdas here too. So I could take this all out. I could say this is my lambda, and I want my lambda to be equal to something called num. It doesn't have to be num. It could be n goes to n mod 2 equals 0 and so on. And that is my lambda. And I could then just do the same thing here. I could just say where this lambda, this delegate. So again, lambdas, delegates, anonymous methods, they're all the same. And you can define them as a method implementation before you use it. So you now have an instance of it, so you can put it wherever that signature is required. And some cases we want to reuse this functionality outside of this one method. You might want to define the actual full-blown method here and then call that directly here. And from the 10 other places you might want to use the same sort of implementation without having to re-implement this over and over. Right? Now if you had multi-line, so lambda statement blocks instead of expressions, then in this case I could do something like this. N goes to open close curly, and over here I could say at that point I have to use the return keyword. So return instead of just doing it without the return here. Right? I don't have a return here. I'm just saying return is implied in this scenario. But the moment it goes to multi-lines, you have to say return n mod 2 equals 0 and so on. So this is a lambda statement block. It doesn't have the word delegate in it. It's following the same rules of lambdas of parens required or not and so on. But it's a lambda statement block. And the single line version is a lambda expression. So if I did that, that's a lambda expression. When it's one line, it's an expression. When it's multi-lines, it's a statement block. So once again, delegates, anonymous methods, lambdas, they're all the same. And when you see something like func in bool, in the case of a func, the last generic type parameter is always the return type. We also have action predefined again. So I could have an action that says, in bool, for example, call it, my action, and I could implement this action in a way that in a lambda scenario. So I could say, well, I want this action to be, so in the case of an action, the second or the last, not the second, but the last generic parameter is not a return type. It is actually incoming. So actions are things that do and return nothing. Funcs are methods that do something and return something. So actions just take incoming parameters but don't return anything. So both of these are incoming parameters. So I could call this I and something bool, right? So let's call it B, just to keep our head straight here. And I could implement this as a lambda statement block. It doesn't have to return anything, so there's nothing for me to actually write here. It's just probably saying I'm not using B anywhere, so I have to use it somewhere. But that's how I would write this inline. So function actions are predefined delegates, if you will, part of the base class library or the .NET framework. And they, again, actions have multiple overloads. They go up to 16. So functions go up to 17 because they have a return type. Actions go up to 16. In other words, you can have 16 incoming parameters. I hope you don't write any method that have so many parameters, but they predefine these for you, so we don't have to define it ourselves. Now, if I need a function, so let's say I define a delegate here, my own delegate again. So delegate, they actually also have defined predicates. So just so you know, there's funcs predefined, actions predefined, there's also predicates predefined, and predicates just taken the one incoming parameter, right? So they define this the predicates type as well. So let's define some method of our own here. Let's call it it returns a bool. Actually, this func mine is good. So it's a bool returning, and it takes an int as a parameter. So I already have this delegate defined. I got this, the signature I wanted, something that takes in an int, returns a bool. And the reason is it's similar to this concept, right? Takes in an int, returns a bool. The where takes a func, specifically a type of func, right? It's not just any method, it's a type of func. So if I assign this to let's say, so my del func here, I make this func mine, right? So instead of changing from a func in bool, I change this to func mine. It's the same implementation, the same signature. One would think that I should be able to use this over here like this, but actually this won't work. It won't like this. Let me take this out, because just because the signatures are the same, they're not the same type. C# is still a strongly typed language, and this type func mine is not the same as func in bool. The two types are not compatible, even though the signatures are compatible. They're not the same type. Therefore, the compiler doesn't like this. It expects actually a func, very specifically a func in bool, or a delegate that is not typed to anything. As in, this is just a delegate. It has the same signature, and the compiler can convert this and produce an instance. Right. So the compiler behind the scenes could do this. It could just say new func int bool, giving it this my predicate as a constructor parameter. You don't write it like this, but that's what the compiler is doing behind the scenes. And so this actually works because of the fact that you're creating a new instance pointing the delegate to this method, but the delegate actually is a type func in bool. It's not a func mine, right? So just keep that in mind. Delegates are not type compatible. The signatures may be the same, but they're not the same type. Therefore, they're not type compatible. Alrighty, so that brings us to the end of this part 2. I hope you've enjoyed yourselves and that I have actually conveyed some information that you did not know of before. That was the intent. And the part 3, the next part, we will be looking at higher order functions and streaming as the key focus points there, and getting us to think in terms of higher order functions when we define our own classes and methods. So I'll see you guys next time.